Hello, everybody. Welcome to the last lecture of first week of our course. In the last lecture, we have already discussed about a few multispectral sensors such as Sentinel-2, Landsat 7, Landsat 8. We have seen like how Landsat 7 existed much back in time, since 1999 or so, whereas Sentinel-2 is much more recent. Whereas Sentinel-2 in terms of spatial resolution provides much richer information, at least for a few specific bands. It provides 10 meter per pixel, which is not the case, right, in the case of the Landsat sensor that we discussed. So with all this background, now let us try to reason a bit about, like, in general terms, about the challenges involved in working with the multispectral images. So here, as I said, like already before, that sometimes we are even just working with, let's say, RGB images. We sometimes in this course we refer to them as multispectral, but here we are, like, when I'm talking about this high dimensionality issue, I'm talking about like more like, like we have Sentinel-2, we have 13 spectral bands, or some other sensor 11 spectral band. So there what we are saying is like we have significantly higher number of channels or bands with respect to, like, if we talk about just RGB images. And this leads to several challenges. I mean, this cursive dimensionality I'll be talking again in the context of hyperspectral images soon, where the number of bands is really, really large. However, also the challenge is in the terms of interpretability, right? Often what we end up doing is like, still not talking about like using a deep learning pipeline. So often most of like the simpler tasks, like let's say we want to analyze vegetation, or we want to understand the patience of water, we just convert this 13 bands or 11 bands to, like that one particular index or channel which denotes this particular information. Of course, this is something you can also do with machine learning or deep learning as well. They are also, in addition, on the top of those 13 bands, you can actually feed as like input to those indices. So yeah, I mean, we have spectral redundancy, and what happens often is that neighboring bands are often correlated. So we saw, right, in the when we are discussing Sentinel-2, like we have now, like, we don't have just one SWIR band, we have multiple of them, we have multiple of NIR bands. So these, for some particular applications, they are helpful for sure, but for most other applications they might be just, like carrying highly correlated data and thus redundant. Now, yeah, I mean, this is of course the aspect which is very important, and the reason that we will later talk about synthetic aperture radar images or active sensor based images. So what we see is that our optical sensors, they are impacted by cloud or other such artifacts, and this means, I mean, when I'm saying that, let's say like this particular sensor, let's say Sentinel-2 or some other sensor is available every 5th day, it's not always the case it's actually available every 5th day. It can often happen, like, let's say we are talking about monsoon time. It may end up happening that the usable, okay, image was not available for the entire month or so. So the actual temporal availability is dependent on these factors. So the illumination variation is another aspect. The images are certainly impacted by the season and all. Spatial resolution, so the multispectral, like the satellite-based multispectral images, the spatial resolution is often quite poor, as we have seen, like in some cases it's 30 meter per pixel. Even the best cases that we saw for this, like, okay, I'm not again like talking about those commercial ones, rather like the Sentinel 2 Landsat and all, like the freely available one, which we will be probably using for most applications. The spatial resolution is quite coarse, right? 10 meter per pixel is often not good for many applications. Depends on the application, of course, but if we are talking about like fine-grained urban analysis, probably this is not a resolution which like gives us sufficient information for many applications. And again, I mean, this is the aspect that I already discussed, that the temporal availability, this can be quite irregular. What can happen is that, okay, like otherwise, let's say this gap is 5 days, but as I said that, okay, for the cloud or other aspects, these images are not available often. So let's say today we got image, next 2 acquisitions got impacted. Then, like, let's say we get in usable acquisition after about 15 days or so. Then, so you see, like the practical gap is becoming 15 days instead of 5 days. And then what can happen is that the next time, like from that 15th day, the next usable acquisition can be again after, like, let's say another 20 days. So today, after 15 days, after 35 days, right? So this, what we see is irregular time series. And often what we need to actually, like when we are doing time series analysis, we may need to actually make this like more regular. So there are like different approaches which one can use. So one can probably, like, let's say you're doing Sentinel based analysis, and probably you also like in addition to Sentinel 2, you also bring in somehow Sentinel 1, the synthetic aperture radar based sensor, and somehow fill these temporal gaps. Or you could do like just some interpolation, which of course is not very effective. So these factors that we already discussed, like seasonal differences. In addition to this, there is geographical differences. So, and optical image, a multispectral image acquired in Munich, capturing the Munich's urban scenario and Delhi's urban scenario, they are quite different, right? So this is another, I mean, this is not just, some of these aspects are probably more prominent for the multispectral images, like seasonal differences, but otherwise like geographical differences and all this is prevalent for the like other sensors. So it's like more like a typical Earth observation problem, I would say. And this is something we discuss in later part of this course in more details. One aspect to understand is that, so we are like, let's say like we are interested to just annotate, okay, this is a building and probably this is visible in the RGB bands already. So since it is already available, like visible in the RGB bands, of course, this is straightforward. Whereas, let's say some particular information is visible more in like one of the SWIR band. So the distinguishability comes from those bands. So this may lead to, like with respect to those particular classes, there may be like, like the annotation difficulties. What I'm assuming here is that like we have someone sitting dedicatedly, that person is paid for this particular annotation task. That's how the annotation is done, right? That's how like large scale data sets have been created in computer vision, often using like platforms like Amazon Mechanical Turk and something. But what's happening is that, okay, like this particular class the person needs to annotate, that's not so well distinguishable in the RGB. So the person needs to actually now probe the other bands, visualize, so make some false color image and visualize the other bands, and then need to understand those aspects, and then only the person can go ahead and annotate. So similarly, of course, another aspect is also with respect to the spatial resolution. As the spatial resolution goes down, like in the case of the coarser resolution images, also often it's a bit challenging to annotate the pixels. It may also happen in such cases. I mean, a pixel actually contains multiple objects instead of just a single object, contains multiple objects. So this is an aspect we will discuss specifically with respect to the our discussion on hyperspectral images. So as I already mentioned, like often what happens is that the typical workflow doesn't involve all the bands. What happens is that let's say you are working for like just some water application, so maybe you just compute that water index that we have seen before. Similarly for vegetation, or rather depending on the application. So let us move ahead a bit and let us talk about more machine learning, deep learning kind of pipeline. Even then, maybe depending on the application, maybe we are working on like entirely urban area. So we are kind of convinced that all those 13 bands, they are not useful for us for the particular like classification that we want to do. We think that the RGB and the NIR, these 4 bands together contain the 10 meter bands, to be more precise. They contain more, like they contain enough information that is sufficient for us. So in that case, what will you do? We will simply take that subset of the bands and we will drop the other bands, and we'll go for our analysis with those particular set of bands. There is also another possibility where you are still using like almost all the bands. Let's say, like, I'm not talking about 13. I mean, of course, out of the 13 Sentinel-2 bands, most of the time you'll not use at least the 3, like that 60 meter bands. They are rather used for like, like to understand like the cloud operations and all those aspects. So let's say the other 10 bands I'm talking about, even there, like what one could do is you could do some kind of band grouping. Okay. So because even if you're using all the those 10 bands, it probably makes sense, like to, as you saw, like, okay, the SWR bands had like some specific kind of property. The NIR bands had some specific kind of, NIR or the red edge bands had some specific kind of property, right? So one could probably apply some band grouping. And this is one example which we'll revisit when we discuss change detection. Specific work is also given in the footnote. So what has been done is grouped into 3 different groups called, or rather 4, like RGB, SWR, NIR, and the wedge. These 4 groups, 10 bands has been divided into these 4 groups, and then like one particular deep feature extractor channel is dedicated for each of these groups. Okay, so before moving on to the other like sensors, like we'll be soon moving to the hyperspectral sensors. However, before doing that, let us quickly revisit some application scenarios that we discussed in previous lectures, a couple of lectures back, and let us think a bit whether multispectral images will be appropriate in those applications. So one question is, how good is your city doing in terms of urban green? Think about this with respect to the multispectral images. We are not talking about, like getting any height estimate or anything. We just want a like a binary kind of map showing, okay, urban green and not urban green, okay, 1 and 0 kind of pixel wise classification, let's say. So one straightforward approach could be just take the NDVI, right, the normalized difference vegetation index. That would probably be good enough. If not good enough, of course we could train some networks and all. However, the question that we are trying to answer at this point of time is more like whether the multispectral, like let's say Sentinel-2 images, okay, let's think a bit more in the terms of Sentinel-2. The next questions also, whenever we are moving out of Sentinel-2, we'll specifically mention that. So Sentinel-2 probably has enough number of like sufficient bands, discriminative bands that will work well for this particular application. Similarly, another question is, let's say the city authority wants statistics of the informal settlement. Again, probably one could use normalized difference built up index. We've introduced this. The question is, will the built up index give you enough discriminability? Because you need to also distinguish from, like the formal settlements as well. And this actually comes a bit also in the context of like spatial context, okay? So there the deep learning comes into play. So probably just an index-based analysis will not be good enough. But Sentinel-2 probably has good amount of information. It doesn't have really enough information, because I will say if we could actually distinguish well the height also, which Sentinel-2 has limited capability there, but height would have helped really, like for the informal settlement distinction from like formal settlement to reasonable extent. So what our verdict is that Sentinel-2 has information which can help us. However, probably other sensors can help us a bit better. A bank wants to keep track of the construction projects it has financed. You'd remember from our discussion before that this particular aspect we were more like this was more about like like the height tracking, and this height tracking is a bit more intensive than the particular example in the previous slide. So this, I strongly doubt how much like Sentinel-2, even though there are like now there are works which has shown some capability of Sentinel-2's building height mapping, but they are more at the coarser spatial resolution level, where they give like a idea of like more of the locality rather than an idea of like very individual buildings, because here I'm talking about like okay, particular building under construction, the nearby buildings have fixed height, so Sentinel-2 will probably not be of much help, or such multispectral images as such. Let's say we want to map disaster like flood. So flood, in a way, to some extent, is related to water mapping, right? So thereby we have discussed indices which are useful for water mapping. So our argument will be like, okay, like we can, of course, use of the Sentinel-1, the SAR, helps us even better with flood detection and all, but Sentinel-2 also has good information related to this aspect. Similarly, let's say like disaster, like earthquake. So then the question arises like, okay, what kind of like monitoring we want to do? Do we want to like do a monitoring immediately after? And also the partially destroyed buildings, they're probably multispectral images do not have sufficient information. However, if our interest is more towards entirely destroyed buildings, and we want to do this audit, let's say like a couple of months after the earthquake has already happened, and which means all the debris have been cleared and all, probably in that case multispectral images would give us, even if not satisfactory, close to satisfactory result. Forest fire. So we have talked about like even we have seen this particular false color composition of particular, if I remember well, is WIR band. So there are bands in the Sentinel-2 basically which can help you with such incidents. Here again, like the forest fire itself can be like two different things that you are trying to detect. One is like once the fire has happened, you are trying to detect the burnt area. The other thing could also be like, okay, like there is an ongoing fire, so their thermal bands from other sensors can be useful. Similarly, segmentation of rice fields. Okay, rather what I mean here is like like segmentation of specific crops, because of course the rice fields itself probably is a bit of like more interesting problem with the water pressures and all. Let's say like let's keep our discussion restricted to like specific crops, and then the question arises whether the multispectral image, it has enough information to do this distinction. We have multiple bands in the like the red edge and all, but think about like having even more fine-grained information there. In that case, won't it be easier, because otherwise like most of the crops, they look probably green, right? The spectral signature, to make a clear distinction, probably if we could have like more finer spectral bands there, our task could have become slightly more convenient, right? So we'll come back to that discussion soon. Now think about like whale population monitoring and think about Sentinel-2. Do you think, Sentinel-2 will be good enough? One is the resolution, then the temporal resolution also is a question. So think about this aspect. Many of the problems which we will be coming more details in the week 2, many of these problems are modeled as image classification, which is often like given a particular scene, like we are talking about a single label for the entire image. Semantic segmentation, label for each pixel. Okay, sometimes these terms are a bit used in an interchangeable way, like hyperspectral classification will come soon. This often like hyperspectral classification is actually semantic, like pixel-wise classification. Whereas in the multispectral, we call classification and semantic segmentation a bit more carefully. Also, object detection. Problems are often defined as object detection, as I mentioned. Like when we will talk about SAR images, we will discuss about the object detection, deep learning architectures. Change detection. Okay, so this is very important for like modeling of problem in Earth observation. Now, with this background, let us jump to the hyperspectral images and think about that particular problem statement that we mentioned a couple of minutes back about this fine-grained crop understanding. As we said already that if we had more narrow spectral bands, probably it would have helped us. And there comes hyperspectral images which capture hundreds of narrow spectral bands. Each pixel contains a detailed spectral signature. This enables more like fine-grained crop analysis or material identification. And this is another sensor which is widely used in the Earth observation. So to understand the differences between this RGB versus multispectral versus hyperspectral, the RGB images, they contain only 3 broadbands. The multispectral sensors, they capture limited spectral channels. Hyperspectral sensors, they capture contiguous spectral bands. And higher spectral resolution thus helps us to have better material discrimination. So, in a way, hyperspectral data, like we're having a 3D cube, the 2 dimension representing the spatial information, the 3rd dimension representing the spectral information. And the applications of hyperspectral imaging lies in the agriculture. I mean, the crop monitoring, I already mentioned this. Another interesting application area where hyperspectral images are used is mineral exploration. Since this the detailed spectral signature, this enables us to distinguish between the minerals. So mineral exploration, or for the known area, like where mining is happening, to understand okay, how the mining activities are going on. Military surveillance is another area. Since again it's related to the capability of the hyperspectral images for distinguishing between the different materials. That's why it enables to keep a track of different materials of interest, of military interest. So with this, let us stop here and we'll take forward this discussion with the remaining discussion with the sensors, and then we'll talk about some techniques with respect to the image classification or semantic segmentation or change detection that were used before traditional, as I said before. By traditional, I mean before the era of deep learning, in the next week. Okay, so let us stop here. Thank you.